Good morning. We will get today to finally to the most important section of this chapter, namely how we introduce the concept of a probability model. So you will see that we need to basically define carefully some concepts before we talk about the probability of an event. Once again, if you have already an intuition of what the probability is for an event, hold that thought for a moment and just focus on the build up of the model. So how we actually define in a rigorous manner what the probability model is. Because I'm saying hold that thought because some of the examples we're going to use, or most of the examples, are extremely familiar, and this is for a purpose, so that we can pull examples of these concepts easily and easy to understand as we move along. To some students, this may seem sometimes kind of boring because we're going to talk about the same type of experiment. But at the end of the day, this is actually helpful when you try to understand when you learn a concept for the first time. And then we're going to have plenty of problems in which the story behind the problem is not a typical one or a textbook example, right? So the textbook examples or the repeating examples that you will see in this chapter are related to tossing a coin, because again, that's a very familiar type of experiment that you can easily imagine, and then you can test the notion that you learn with examples like this. Rolling a die, that's another typical example to use. The next one might not be so familiar to some of you, but you'll get to that. I mean, if you like to play cards, this will come a little bit easier. If not, no big deal, you'll learn. Events or experiments related to card games. And we're going to use the typical card deck that most people know about. Another type of example will be, for instance, extracting a ball of a certain color from a box containing balls of various colors, or marbles. Okay, so let's see first of all what we mean, as the title says, what we mean by a sample space. So the whole story of probability theory starts with an experiment. So you have at the beginning of everything a so-called experiment, which can be any so an experiment which can be any action, if you want, that results in a number of outcomes. But the certainty of what outcomes shows up, it's not. So I mean, in other words, you don't know with precision what the outcome is going to come up when you perform that action. So in other words, there is a certain likelihood of each outcome. So we have the experiment, and then what we call a sample space is the set. And remember, we talked about the notion of a mathematical set in the previous sections. So the set of all possibilities that result or that occur as a result of an experiment. And I like to go over quick examples as we introduce these notions right away. So for example, if the experiment is rolling a die, you can actually visually describe the outcomes or the sample space. Sample space, by essentially drawing we're not going to do that, but just to illustrate by drawing what you see when the die stops rolling, right? So you can have the face with 1 dot, the face with 2 dots, the face with 3 dots, 4 dots, 5 dots, and finally 6 dots. Okay, so this is if you want to be visual, right, to illustrate what the sample space is if you roll a die. But you can quickly see that it's far more practical to use other labels, in this particular case, numbers. So the outcomes or the sample space for rolling a die are essentially the faces with the numbers 1, 2, 3, 4, 5, and 6. So whenever I like an example with a decent number of outcomes, not too many, not too few, I can think about rolling a die. So again, sample space should cover every possibility. This is important to understand. When we talk about the sample space, that should cover all possibilities or all results of that experiment. Otherwise, it's not a sample. It's not a complete sample space. Here's another example of an experiment tossing a coin. The sample space, of course, is going to be either heads or tails. Sometimes you may want to also use numbers, 0, 1 or 1, 2. But this is only if it's necessary, really. I mean, because sample spaces with 2 outcomes are essentially binary systems. Binary systems in which you always have one or the other. There's just 2 possibilities. Sometimes you can assign numbers like 0 and 1. We're not going to do that too often because it's not actually necessary. But again, in the case of tossing a coin, you can think of the outcomes being heads and tails. And many other examples, like I said. So this is the sample space of an experiment. So remember, we start with an experiment, and then based on that experiment, we have always a sample space which essentially shows all possibilities that occur as a result of that experiment. And another definition, just to make it clear, each of these possibilities, so each of these possibilities that result from an experiment is called an outcome. Okay, this should be very intuitive, right? I mean, you have an experiment, you have an outcome that comes from that experiment. So each experiment can have a number of possible outcomes. So 1, 2, 3, 4, 5, and 6 are the outcomes from rolling a die. Heads and tails are the outcomes from tossing a coin, and so on and so forth. Sometimes the outcomes are not even talked about too much because you always talk about in terms of groups of outcomes. You will see later when we or events when we deal with some other examples. For instance, in the case of social analysis, for instance, for various data, you'll see an example at the end of the lecture, for instance, in terms of what will be the probability of a family picked at random to have a certain income. So for example, if I want to figure out the likelihood of a family to have a certain income, in that case, the experiment would be picking a family at random from a group of families. That could be at the level of a country or at the level of a town, and so on and so forth. So of course that each outcome is going to be one family. right? I mean, in other words, for example, if a town has 5,000 families, then of course each outcome for each family is a possible outcome of the experiment. And there's 5,000 of them, obviously, right? If that's the universe of the problem, so to speak, right? I mean, if that's the number of families you're talking about in that town. So we have the experiment, we have the sample space. Let's finally move now to what we mean by the probability of an outcome. And you have to understand, we're going to move on the second page to do that in a minute. You have to understand that basically we need to start with some assigned probabilities. So in order to actually use probability theory, we need to actually know the likelihood of each outcome. Okay, I mean, is it each outcome equally likely? And if it's not, how much more likely is one outcome versus the other? We need to know, in other words, from the beginning, the probability of each outcome. That's very important to understand. So we can't build a probability model until we actually assign, by our knowledge, of course, of the phenomenon, the likelihood or the probability of each outcome. So to anticipate a little bit, for example, if I have a fair coin and if I toss it, then I need to actually start by saying, okay, heads or tails are equally likely. So I'm gonna know exactly what is the probability of obtaining a heads and the probability of obtaining a tail if I flip a coin. So the probability of outcomes themselves is already defined is built in the model. Later on, the probabilities of other entities called events, as you also, I'm going to define that immediately. Those can be computed, of course, once we know the probability for each outcome. So stay tuned for the second page when we move on to the definition of the probability of an outcome. All right, so like I said before, the probability of an outcome. So let's see how we build that in. And let's actually use some generic notation now. So suppose we have an experiment with n possible outcomes. If there is some background noise, sorry about that. There's something going outside, some working. So suppose we have an experiment with n possible outcomes. So that means the sample space can be written as S equals the set made of E1, E2, En. This is a typical notation for each outcome. So E1, E2, En, these are all outcomes of that experiment. Like in the previous case with the rolling a die, you can think of E1, E2 up to E6 as being 1, 2, 3, 4 up to 6. So if that is the sample space of all outcomes, right, then each outcome is assigned a number denoted by P of E1, P of E2. It's like a function, P of En, meaning the probability of each outcome, which describes the likelihood of that outcome to happen. So each outcome is assigned a number that denoted by P of E1, P of E2, P of En, meaning the probability of each outcome. So there are some conditions to be met here. So that's very important, okay? So first of all, each outcome, each probability is numbers is greater than or equal to 0. And very importantly, slow down for a moment, always use the pause to catch up, because I always write quickly, but I'm expecting you to use some pause to catch up. Very importantly, the second condition is that the sum of these numbers, the sum of the probabilities of all outcomes should be equal to 1. Think of 1 as the probability value that basically denotes certainty. Now, if you look carefully of these two conditions, that each of these numbers should be positive and the sum of them should be equal to 1, that means that each single probability is going to be a number between 0 and 1. Could be 1 or could be 0, but nothing outside of this range. Which you kind of know already from your common knowledge, right? I mean, if someone is asking you, what is the probability of end up with a heads, if you toss a coin, you will immediately probably say 1/2. And we'll get to that immediately. But what you did in your mind, you basically assign a probability to each outcome, in this case 1/2. But the sum of them is 1, because no matter what you end up with when you toss a coin, it's going to be either heads or tails. So when you add the probabilities of all possible outcomes, we must have, that summation must be equal to 1. 1 is essentially the probability denoting certainty. We'll get to that immediately. If any of these conditions is not satisfied, that's not going to be a valid probability assignment for these outcomes. So again, as an example, let's say we have a fair die, meaning that each face is equally likely to come up when you roll a die. Well, if each face is equally likely to come up, that means so we the outcomes are 1, 2, 3, 4, 5, and 6. If each is equally likely, that means the probability of each of them, P of 1, P of 2, P of 3, P of 4, P of 5, P of 6, all of them should be equal to each other. Now we know already they are equal to 1/6, but let's pretend we don't know, right? Let's pretend we build this model from scratch. So we roll a fair die. We know that each face is equally likely to come up. So then we have to come up with some probability assignments for each outcome. How many outcomes do we have? We have 6 possible outcomes. If each of them is equally likely, the probability of each of them should be equal to each other. Let's pretend we don't know what it is. Let's call it X. But to be a valid probability assignment for this model, the sum of all of these probabilities, all 6 of them, should be equal to 1. So that means 6x equals 1, x equals 1/6. So there you go. That means the probability of each of them should be 1/6, as you knew already. But I'm illustrating how you do this basically in more complicated problems when we don't exactly know, and I'll show you an example immediately, when it's not going to be that easy to guess what each value is. But again, based on the knowledge, if we have complete knowledge about the likelihood of each outcome, then we should come up with a probability assignment that is correct. If someone says, you roll a die, and let's call this example 1, example 2. Let's say you roll a die, and someone says the probability of having 1 is going to be 1/2, probability of 2 is 1/2, probability of 3 is 1/4, probability of 4 equals 0, of 5 equals 0, of 6 equals 0. Now, you may say immediately, well, that's not valid because, shouldn't be equally likely, because if I roll a die, each face is equally likely. Now, I didn't say a fair die. Let's say this is a loaded die. Loaded die meaning that, the center of gravity, for example, of that little cube, the die is in such a way that some faces are more likely than others. Now, so it's not a problem that each outcome is not equally likely. That's not what makes this invalid, because by the way, this probability assignment is not valid. What makes it invalid is that it violates the condition that the sum of the probability of each outcome is equal to 1. If I add up all of these probabilities, I get 1 plus 1 over 4, which is 5 over 4, and that's not equal to 1. All right, so it is one condition when you assign the probability that the sum of each, or the sum of the probabilities of all outcomes should be equal to 1. And we're going to continue with some other examples on the second page, so stay tuned as we move along. So let's talk about example 3. Let's say the experiment is tossing a coin, tossing a fair coin, let's say. Then of course the sample space will be heads and tails. If I say a fair coin, each is equally likely. And then obviously if they have to add up to 1, pretty obvious that the assignment of probabilities of each outcome should be 1/2 for each outcome. And P of H plus P of T obviously is equal to 1. You could have, let's put example 4, you could have such a loaded coin that it always comes up heads. Well, in that case, of course, the probability of heads is equal to 1. The probability of tails is equal to 0. So probability equal to 1, that means a certain event. Probability of equal to 0 means the event is impossible. Obviously, you don't want to play the game at the casino with such a coin. Unless, you know, of course, well, let's not get into the cheating at the casino. But again, I want to focus on the math part of it. There's nothing wrong with this type of probability model, right? I mean, it doesn't contradict the reality or any mathematical condition. As long as these probabilities are between 0 and 1, and they add up to 1, when you add up all those outcomes, then that's a valid probability assignment. This is an obvious loaded coin. Let's say that you have a loaded coin in which, let's say the heads are twice, or the heads is twice as likely as tails to come up. And again, you may guess what the value is for the probability. Let's pretend we don't know exactly. So if tail and heads, and if heads is twice as likely, let's say the probability of tails is x, and the probability of heads then is 2 times x. So, okay, all we know about the experiment is that the heads come up twice as, it's twice as likely to come up than tails. So what is the correct probability assignment? Well, let's call x the probability of tails. 2x has to be the probability of heads, twice as likely. Nevertheless, the sum of the two should still be equal to 1. And that means x is equal to 1/3. So therefore the probability of tails is 1/3, and the probability of heads is twice as much, obviously, 2/3. So that will be a probability assignment for a loaded coin. Sometimes these number of outcomes takes a little bit of work to figure out, and we're going to have plenty of examples to deal with today before we call it a day. So here's another example. This time, let's say you decide to throw 2 coins or toss 2 coins. So let's say the experiment is tossing 2 coins. Sometimes the problems are a little bit confusing in the sense that Do they mean I actually have two physical coins? Or let me actually write in parentheses here, tossing a coin twice. Basically, if I formulate the problem in such a way, I basically refer to the outcome of the two coins at the same time. So if I talk about the outcome, I think of what comes up on both coins on each instance, then these two are indistinguishable, right? So these two formulations are the same, whether you toss two coins or one coin twice, but you always refer to the outcome as a pair in the sense that what came up twice, then the distinction between the two doesn't matter. It gets confusing, especially if you talk about what happens with each toss. That's a different thing, right? So if I say I'm tossing a coin 2 times or 3 times, what happens on each given toss? What's the possible outcome? It's still heads or tails. You can toss the coin 1,000 of times. If the question is what comes up on each toss, the experiment is still tossing one coin. Doesn't matter if you repeat the experiment 1,000 times. If the question is about what comes up when you toss a single coin, that's the experiment. But if I say I toss the coin twice, what's the outcome? Then obviously I'm talking about what's the outcome on those two tosses, or equivalently, if I toss 2 coins, again, what's the outcome in that case? So that has implication in terms of the number of outcomes, because if you talk about 2 coins or a coin tossed twice, then you have in fact 4 possibilities. So a sample space will be heads heads, heads tails, tail heads, tails tails. So you have 4 outcomes. And again, if let's talk about tossing a coin twice, right? So let's focus on this second formulation. If that coin is fair, then again, each outcome is equally likely. So there's 4 of them, and obviously in that case, the probability assignment will say that the probability of each of these outcomes should be 1/4, obviously. But let's say we have the loaded example as in 5. Let's say as in 5, so what if the coin is twice as likely to come up heads? So this sometimes can be a little bit tricky in terms of how you actually figure out the probability assignment. Now, clearly, if you look at the outcome, so let's focus here on the set of outcomes. And pause for a moment and think about which is the least likely outcome. So really pause the video for a couple of seconds or a minute and think about which is the least likely to happen. Maybe which one is the most likely to happen, or anything in between, basically. So I mean, actually, yeah, just figure out which one is the least likely to happen, which one is the most likely to happen. If I see that this coin that I tossed twice is twice as likely to come up heads. Okay, so if you actually thought about for a moment, when you pause the video as I ask you to do, if the coin is twice as likely to come up heads, obviously this is the least likely. So let's call the probability of double tail as X. Now, the second and the third are twice as likely because one single coin is twice as likely to come up heads. And because each coin is twice as likely to come up heads, this guy here is actually 4 times as likely to come up. So when you put this thing together, that means a probability assignment that satisfies this this assumption of the loaded coin is that x plus 2x plus 2x plus 4x should be equal to 1, which makes 9x equals 1, so x equals 1 over 9. So basically, in this loaded coin, the probability of double tail is 1 over 9, the least likely outcome. The probability of 1 heads and 1 tail is going to be twice as likely, which is 2 over 9, right? 2 times x. And the probability of 2 heads is going to be 4 over 9. Basically, you'll see later, there is a formula actually we can deal with when you actually multiply the probabilities. If you think about the previous example, you know, the fact that the probability of 1 head is 2 over 3, the probability of 2 heads in tossing that coin twice basically is going to be 2 over 3 times 2 over 3. That's why you end up with 4 over 9. So we're going to have actually a easier way to formulate this or to compute these probabilities once we learn some formulas later on. But for now, we just look at the intuition. There is a homework problem, by the way, in which you are given some example of sample spaces, and you're asked, for example, which one shows a loaded coin for which one side is twice as likely to come up than others, and so on and so forth. So with that in mind, let's actually finally talk about another important definition, and then we finish up with other examples, namely the definition of an event. And then after that, we'll finish with examples. So stay tuned for the next page. All right, so before we define what an event is, let's put things together, all the things together that we discussed previously. So what do we mean by a probability model? So remember, we start with an experiment that has a set of possible outcomes, the so-called sample space. We assign probabilities of these outcomes such that the sum of these probabilities is equal to 1 and each of them is positive. So this is what constitutes in mathematics a probability model. Experiment, sample space, assignment of probability for each outcome. Now, often we ask other questions based on this experiment rather than the probability of each outcome. Because if we are only interested in the probability of each outcome, things are not that interesting, right? Because we already know the probability of a single outcome. The idea is actually to figure out the probability of other types of situation, if you want, that can come up from running this experiment. So in other words, you want to ask different questions based on that experiment. And we're going to illustrate this immediately once we define the notion of an event. So that's going to be the last definition for today. So an event in the language of probability is a subset of the sample space. So basically is a set of outcomes, not a single outcome necessarily. So let me illustrate why you might want to know, for example, why you care about the probability of an event, or why you care about events in the first place. So let's go back to the rolling a die experiment. For example, you may want to figure out how likely is to obtain an even face. So notice, let's say you don't care about whether you get a specific number. The probability of getting a specific number is 1 over 6, we know that. But what about an even face? Let's say you play a game in which there is some prize if you roll a die and you obtain an even face. That is a question about the probability of whether you end up with an outcome in the following set. 2, 4, and 6. Okay, so an even phase is essentially an event because this is a subset of the sample space for rolling a die, which is made of 1, 2, 3, 4, 5, and 6. So it's a combination, basically, or a collection of outcomes, not necessarily all of them, right? I mean, obviously, the probability, just to make it clear, the probability of S is always 1, remember? So, I mean, because the sample space covers everything, then, of course, when you roll a die, you're certain to obtain 1, 2, 3, 4, 5, or 6. But then, if I want to know the probability of a subset of these outcomes, then we need a slightly different definition of the probability, which is based on knowing the probability of each outcome. So an event, like I said, and is usually denoted by E or other capital letters of the alphabet. And I actually lied because that's my final definition. I said that the event is the last definition. We're going to define the probability of an event E as being, so the probability of E has been the ratio between the number of outcomes in the event, in that subset, divided by total number of outcomes. In the sample space. So in my example with rolling a die, the probability of that event is equal to the number of elements in the event itself, which is 3, divided by the total number of outcomes, which is 6. And surprise, surprise, everybody knew that already, the probability is going to be 1/2 because we have 3 even numbers, 3 odd numbers. So the probability of ending up with an even number is going to be 1/2. And you can basically, what we're going to do basically from this point on, we're going to compute probability of events, and we're going to use special formulas when these number of outcomes is not easy to count. This is essentially the whole crux of the matter. If it was easy to compute the number of outcomes in the event, in all cases, and the total number of outcomes in an experiment, you don't need much of a theory, so to speak. You just basically get that number and make a ratio. But in many situations, the practical ones, right, not just rolling a die, things are not that easy, or they can be quite tricky in terms of counting the outcomes. So you need formulas to count the outcomes, or formulas that build larger probabilities of larger events from smaller events, if you want. So that is the whole idea from this point on. Let's move on with a couple of more examples just to fix the notion here. Let's say also with rolling a die, so I'm going to use the same experiment here. Let's say I want to know, let's say the event A is obtaining a number greater than or equal to 5. So I describe the event obviously in words, but since we know the possible outcome satisfying this condition, obviously the event A is made of 5 and 6, because if you roll a die, those are the numbers greater than or equal to 5. So just like before, based on the definition, the probability of A is equal to the number of outcomes in the event, which is 2, total number of outcomes, which is 6. You can simplify that to 1/3. Maybe it's a good idea actually to talk about the card deck, just to have it here. So the standard card deck, because I'm going to use that also for some examples. Those of you who are familiar with this, you can skip that if you want, or just watch it just to make sure we are on the same page. If you don't play much cards, then that's fine. You just basically, well, maybe you can buy and you can start playing a little bit, right? I mean, it's fun. Who knows? Maybe that's going to be a useful hobby, given the current events. So standard card deck. You have basically certain figures, right? So you have essentially cards with a number or a figure, and each figure or number on a card has 4 suits. So we have basically in total 13 face values, which are either number or figures. So the face values are 2, 3, 4, 5, 6, 7, 8, 9, 10. Then followed by the ace, the jack, the queen, and the king. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So 13 face values. Each face value card has 4 possible suits, which is basically just a little symbol attached to each face value. So the possible suits are diamond, which is red. Then we have the heart, which is also red. And we have the clubs, which is black. And the spade, I'm not too good at drawing stuff here, which is also black. So you're going to have questions like this. The card deck is nothing special about it, but it's another very useful standard example for a slightly more complicated question. Because I mean, with the rolling of a die, you kind of exhaust the number of possible questions. If you want to get a little bit harder than that as a standard model or a standard example, that's not useful. That's why another type of example is related to, for example, to those balls of different colors in a box. But the card deck is also useful because it's familiar to at least most of you, if not all of you. So for example, okay, and by the way, the number of outcomes, right? So I mean the total number, so if the experiment is picking a card at random, then the number of outcomes possible is 13 times 4, which is 52. So there are 52 cards in the deck. 13 face values, each of them has 4 suits, so in total 52 cards in the deck. We're not going to deal with the jokers. I mean, we're not going to include those in our standard examples. So we define what an event is. I think we're going to move on to the next page with lots of questions, couple of questions in which we count the elements in an event, excuse me, in not events, the number of outcomes in an experiment, and then some other practice questions with finding the probability of various events. So stay tuned for I think it's going to be the last page, but we shall see. All right, so let's go over a couple of examples in terms of finding the number of outcomes in an event, in an experiment. So let's say, let's say the question here in all of these examples. So the question is number of outcomes in the following examples. So let's actually start the count from 1. So each will describe an experiment. You have to find the number of outcomes. So let's say I want to tossing a coin 4 times. Now you can make some connections with the previous lessons, the multiplication principle, if you want. If you toss a coin 4 times, that means you have basically 4 slots, right? With each of them with a number of possibilities depending on whether each coin lands heads or tails. Heads or tails, heads or tails. Now, what I want you to aim for is not to actually sketch or write down all the possibilities like I did here, but just to realize that each toss has two possible outcomes. So if you toss it 4 times, then by the multiplication principle, the number of outcomes is 2 times 2 times 2 times 2, which is going to be obviously 16. So as you notice, many problems in this chapter don't require too much work. Just make sure you're correct, because there's not much room for partial credit, basically. So multiplication principle, remember, it was defined as a selection of, a couple of items. Each item has a number of possibilities, and you multiply those and you get the total number of selections. You have to be very careful about wording here. So I toss a coin 4 times. Each of them has 2 possibilities, heads and tails. So of course we have 16 possibilities. But sometimes you see words like with or without replacement. So here's a quick example. So suppose you have a box with 10 marbles. Okay, so now I describe the experiment, part A. The experiment is picking 2 marbles with replacement. That means I pick a marble, I put it back, I pick another one at random, right? So you have picking 2 marbles with replacement. I didn't finish the phrase here. From a box, I said it, sorry, I didn't pay attention. So we have 10 marbles. I thought I didn't mention 10. So you have 10 marbles. We pick one at random, we put it back. That's what we mean here by with replacement. And then we pick another one. Obviously, you have a selection of 2 possible, a selection of 2 items, a marble picked at random. The number of possibilities is 10 for each of them. So it's 10 times 10, which is 100, because you put it back. So each time you pick a marble, you have 10 to choose from. So then you have 100 possible outcomes. But if I say, for the same box, that I'm going to pick 2 marbles without replacement, the number of possibilities for the second selection is not going to be 10. So for the first selection, I have 10 marbles to pick from, but I don't put it back in the box. So when I make the second selection, I have 9 to choose from. So by the multiplication principle, we have 90 possible outcomes. So it's very important to to pay attention to the way the experiment is worded, so that you can find correctly the number of outcomes. And then let's talk about actually computing some probabilities. So here's actually one experiment, and then a couple of questions based on that experiment. So suppose that we have a box that contains, I'm gonna illustrate that box here, 3 white balls, 8 blue balls, 5 red, and I don't have room here, and then 7 green balls. Okay, so just imagine that they're all mixed up. 3 white, 8 blue, 5 red, and 7 green. And then the experiment is a ball is picked at random. And here are a couple of questions. Let's say, and by the way, in terms of the event, in terms of the outcome, the number of outcomes, well, let's see, it's 3 plus 8, 11, plus 12, that's 23 outcomes. So each outcome if it's equally likely, okay, so you pick a ball at random, each of them is equally likely to be picked, the probability of each outcome is actually 1 over 23, right? So there's nothing in the problem that suggests one ball is more likely than the other to be picked up. So again, it's very important to fix your data here in terms of the probability model. What is the probability model? We have an experiment which says a ball is picked at random. How many balls we have? 23, so we have 23 outcomes. Each of them is equally likely to be picked up. That means the probability of each outcome is going to be 1 over 23. But that's not typically what the question is. What you have are questions on events. So for example, question 3, you can be asked, what is the probability that a green ball is picked? And so in that case, of course, you look at the number of, so this is going to be an event, right? The event is basically all the outcomes that constitute green balls. If I look at the number of green balls, that's 7. So according to the definition of the probability of an event, the number of outcomes in that event is 7 because I have 7 green balls. And then the total number of outcomes is 23. So then you have 7 over 23. What if they say red or white? So what if the question is the probability of a red or white ball is picked? Well, how many red ones do we have? Well, we have 5 red ones and 3 white ones. So the number of outcomes in the event red or white ball is going to be 8 divided by total number of outcomes, 23. Again, pay attention to the wording. Let's say, for instance, the question is, what is the probability that neither red nor green is picked? Well, anything but red or green, right? So if I have, so what is everything else? Everything else is going to be, if you look at the box, is going to be 3 and 8, right? 3 white and 8 blue ones. So neither green nor red, that means 11, right? So 3 plus 8 over 23, that's 11 over 23. All right, so you have some similar examples in the homework. Let me finish with a slightly more well, not more practical, but more down to earth or from real life example. Sometimes you can find probability of events based on tables. And often we can, if we understand very well how the probability theory works, we don't really have to specify the number of outcomes or what the probability model is, because it's kind of implicitly understood. Only when it's kind of a risk of making a mistake or not setting up the data carefully to begin with, only then you can slow down a little bit to make sure you answer correctly. But often the structure of the probability model is very easy to, it's so obvious that you don't even need to specify it. So let me illustrate what I'm talking about here. So suppose you have basically in a town, let's call this example 6. So you have a town of 3,000 families altogether, including single living people, right? So you have 3,000 families, and let's say you have a data breakdown over the income of these families. So I'm going to actually write it here on the right side here. So let's suppose you have a 2-column table with the income level and the number of families that meet that income level. So let's say less than $25,000, we have 700 families. And then between 25,000 and $50,000, let's say we have 2,000 families. And then greater than $50,000 income, we have only 300 families. And let's say the question is the probability, or find the probability of a randomly selected family to have an income let's say above $25,000, or including, yeah, so greater than, or let's be precise, right? So greater than or equal to $25,000. I want to be picky here with greater than or equal to, because, for example, it's important to know in which row of the table the breakpoint 25,000 is included. So if I say strictly less than 25,000, that means 25,000 is included in the second row. So between 25 and 50,000, and including those endpoints. So see, you don't actually need to be formalize this type of probability model too much, right? I mean, like, for example, what is the experiment? Well, it's kind of mentioned in the problem, right? A randomly selected family. So the experiment is mentioned in the problem already, right? You pick a random a family at random from the data points, right? And then, and by the way, what is the outcome? Well, each family is the outcome. If I pick at random a family out of 3,000 family, then of course each family is an outcome. What is the probability of each outcome? Well, if it's equally likely to pick any of the families, it's going to be 1 over 3,000. But that's not the important or interesting question, right? It's just basically already implicitly understood that if there's nothing special with you picking the family, each outcome is equally likely. Okay, so I have 3,000 family, each of them is equally likely to be picked. But the question is about not an outcome, but an event, which is a subset of outcomes, right? I mean, how many, well, what's the probability of an income greater than or equal to 25,000? Well, the number of outcomes in that model, in that event, well, I have to look at the table and I have to say, okay, above 25,000, including 25,000, I have 2,000 in that income bracket, plus 300 in the income bracket above 50,000. So I have in the total 2,300 families in that income bracket greater than 25. Divided by the total number of outcomes, which is the number of families themselves, that gives me 2,300 over 3,000, and you can simplify that a little bit. So 2,300 over 3,000, and that's going to be 23 over 30, right? The probability of a randomly selected family to be to earn more than $25,000. So you have a similar problem in the homework, but with a more breakdown, essentially, of the income brackets, right? So it's all about counting the elements in that event over the total number of outcomes. So with that, I think that's it for today. Make sure you don't move on until you learn or understand every single example in this section, because it's going to be much easier if you do that. If things are shaky right now, you're going to struggle for the entire chapter 7 and 8. So make sure you bring all the questions you may have during the office hours. And that's it for today.